Hello, my name is Rupali, and it is a pleasure to present this work carried out under the guidance of Dr. Menak Adhikari. This work is titled as Multiview Ensemble Federated Learning for Efficient Prediction of Consumer Electronics Applications in Fog Networks. In this work, we propose a multi-view ensemble FL framework for consumer electronic applications in fog networks, namely EnsembleFed. The proposed approach derives multiple views from raw data to gain deeper insights from it and trains a model for each view. Later, the output of these models is assembled for robust predictions. The distributed fog nodes are incorporated in the FL framework to combat single point failure risk and improve communication efficiency. The figure here demonstrates the system model of our proposed framework. It consists of multiple sensors with some sensing capabilities by which the data is retrieved from the environment. The set of sensors send the local monitoring dataset to the connected edge devices in the network. Each edge device divides the acquired dataset into three different views and applies the model to train each of the data views. These edge devices send the local model parameters to the connected fog nodes for local model aggregation. These locally aggregated model updates are then shared by the fog nodes with the central server C or elected global fog node for global model aggregation. The goal of federated learning is to train a global model that can accurately predict the labels of an unseen dataset. Next, the globally aggregated model updates for all the views are communicated back to the edge devices for further training, and the cycle continues till a certain level of accuracy is achieved. The figure illustrates a detailed view of multi-view ensemble federated learning framework. Initially, each edge device parallelly trains three different models corresponding to the three views of the dataset for a certain number of epochs. In our case, we divided the dataset acquired from the sensors into three different views, that is the data views. So, we train three different models, that is one model for each view. After completion of the training process, the edge devices ensemble the model outputs of all three views to predict the actual output. During the ensemble process, the edge devices compare their individual prediction with the final ensemble prediction. This validates if there is any data hampering that is causing the deflection in the prediction and increases the prediction accuracy. A count variable is maintained for counting the deflections, and if this count exceeds a predetermined value of threshold, it indicates a warning to check the sensor health and site disturbances, if any. This precautionary step also prevents the model from learning from defective data, thereby increasing its accuracy further. After completing a local iteration of model training, each edge device shares its locally updated model with the fog node present in its geographically close vicinity. Each fog node then parallelly aggregates the model updates for each view specific model from all the edge devices connected to it. The incorporation of fog nodes in the FL framework promotes parallelism in the training process and relaxes the computational and communication burden on the central server. Firstly, parallelism is achieved as multiple fog nodes concurrently perform model aggregation near the clients. Secondly, since only the fog nodes further connect with the central server for for model aggregation, the central server needs to aggregate a smaller number of models of the fog nodes as compared to the models from each edge device. This improves the communication efficiency as the central server establishes a connection with a few members of the fog nodes rather than many individual edge devices or clients. Each fog node shares its updated aggregated model parameters with the central server or elected global fog node for global model aggregation. The globally aggregated model updates are then circulated to all the edge devices for further training process. The edge devices continue to train these models corresponding to three different views and keep sharing the local updates for aggregation until a set level of accuracy is attained. The aggregation at the fog level and the global level happens for each of the three models corresponding to three different data views. The process of global model aggregation is performed after every n number of local iterations. This reduces the burden on a central server and increases the communication efficiency of the system. In this figure, we represent the multi-view ensemble training. The multi-view ensemble training comprises of three basic steps, that is creation, evaluation, and ensemble of data views. Creation of data views. Several evolutionary algorithms can be employed for creating data views using feature selection to derive more insightful information from the ML training process. However, supervised formation of data views is more efficient than random formation. So we divide the features into different views for better analysis and demonstration of efficiency achieved by the proposed EnsembleFed approach based on the geographical area from which the data is derived. Evaluation of data views. In the evaluation phase, each edge device trains a separate model corresponding to each view of the dataset obtained from the raw data. Each model structure comprises of an input layer, hidden layers, and an output layer. The input dimensions, which is the number of inputs for each model, is obtained based on the input feature count from each dataset view. Then the third step is the ensemble of data views. Ensemble learning helps in increasing the accuracy of the predicted output. We perform the ensemble process for the prediction obtained from three distinct models specific to each view that are trained in the evaluation phase. After the ensemble process is completed, we find out if there exists a difference in the prediction. The difference in the predictions beyond a certain number of predictions is considered a sign of faulty data from the sensor. Thus, besides improving the system accuracy, the ensemble process also helps to identify any instructions or hampering of the data. The figure here illustrates how incorporation of fog nodes achieves dimensionality reduction. The incorporation of fog nodes in federated learning framework achieves an optimal distribution of model aggregation tasks across the network between the cloud server and the edge. The idea is to traverse the model aggregation task through a fog layer which encompasses of fog nodes placed closer to the edge devices. So parallelly, the edge devices model updates are aggregated near the edge and the aggregated model updates are transferred upstream further from the fog layer to the central cloud server for global model aggregation. This achieves dimensionality reduction in the messages being transmitted upstream over further distances. Figure represents the experimental setup that we have uh, set up to validate the performance of ensemble-fed approach and justify its superiority. We have basically implemented a smart irrigation system prototype employing the proposed algorithm. We compare multi-view and single view and multi-view performances. Multi-view converges better than single view. The convergence depends on the diversity and the accuracy of predictions from different views, which affect the bias and variance. Thus, there may exist an optimal level of diversity and accuracy of the predictions from different views that maximizes the benefit of using an ensemble method and ensures that the convergence converges to a near optimal solution. Figure demonstrates the communication overhead during the model transmission. Communication overhead can be reduced by minimizing the model parameters transmission between the client and the central server. In EnsembleFed, fog nodes are placed between the clients and the central server to reduce the transmission delay of model parameters, which further reduces the communication overhead of the network. Figures represent the comparative analysis of the proposed ensemble-fed approach and the existing standard FL versions in terms of communication overhead on uploading the updated model parameters and downloading the aggregated global model parameters. The results show that the communication overhead in the proposed ensemble-fed approach is less than the standard FL techniques. We also empirically show the superiority of ensemble-fed approach over the state-of-the-art FL techniques and showcase how the proposed approach improves the system resiliency and robustness. We have compared the performance of ensemble-fed with state-of-the-art FL versions, namely Fed Yogi, Fed Adapt, and Fed Average. The figures or the plots of accuracy and training loss indicate that the ensemble Fed clearly outperforms the existing state-of-the-art FL models or frameworks. Thank you.